In this lecture, we'll be talking about recycle and bypass streams and chemical process flow diagrams. Earlier in the class, we talked about the standard or typical chemical engineering process flow diagram. It's reproduced here. In a typical chemical engineering process, raw materials are fed to a reactor or transformer in which the raw materials are converted into a product of higher value, a product that's used to fulfill some human need. Unfortunately, in this transformation process, not all the raw materials are converted to products. So we have residual raw materials, leftover raw materials. We also, unfortunately, may produce some unwanted byproducts. So in order to purify the desired product from the leftover raw materials and from any undesired byproducts that might be present, the reactor is followed by a separator. And the separator will remove the desired products, purify them, and then the undesired products are removed as a second stream. And these could be treated as a waste. If they're treated as a waste, then the raw materials that we fed to a reactor will be sent to a waste stream and we'll lose the value of those raw materials. A preferred way, both economically and environmentally, is instead of separating out only the desired products, is to separate out in the separator the unreacted raw materials as well as any catalyst that might have been used to enhance the reactor. A catalyst is typically added to accelerate the rate of reaction or to make it more specific. And we'd like to be able to reuse that instead of sending it through just once and then having to buy more catalyst. Now, this stream, the separation process and the recycle of the stream is the nature of a recycle stream. And this is what we commonly see in a chemical process, is that there'll be one or more recycle streams to recover unreacted raw materials or catalysts or for other purposes. For instance, it could be used to dilute the feed to a reactor, to help control a reactor, or there might be a working fluid that's recirculated around, a fluid that's used to transport materials through the process. Here's an example of a process to make methanol from carbon dioxide and hydrogen. Now, you might think of this as a process in which we can take CO2 from the atmosphere and convert it into a fuel. This is something people are talking about, trying to use CO2 as a raw material. One of the challenges with this particular process is that if you're using hydrogen as a second reactant, is that the hydrogen, the current sources of hydrogen are primarily from natural gas. And so we are going to be using a fossil fuel in order to convert CO2 into methanol. And so ultimately, if you were to consider using this process for making fuel out of CO2 from the atmosphere, you'd have to consider the impact of the hydrogen production from methane, from natural gas. And if you look at this process, the streams are all labeled with a flow rate and composition. From the feed over here, the feed to the far left, which flows in at 60 kmols per hour and has a composition of CO2 of 25%. It's 75% hydrogen, and this hydrogen helps drive the reaction to methanol. The excess hydrogen does. In the reactor, well, the feed stream is mixed with a recycle stream from the separator, which flows from the separator back to the feed to the reactor at a flow rate of 40 kmols per hour. Note that the magnitude of that recycle stream is almost equal to the magnitude of the feed stream. And the recycle stream contains more carbon dioxide on a mole fraction basis than the feed. The mixture of these two streams that goes into the reactor flows in at 100 kmols per hour and contains a little bit more carbon dioxide than the fresh feed that comes in, the 60 kmol per hour stream. After the reactor, we now have present in the stream methanol and water, both present at about 21%. What we want to do is separate the methanol and water from the stream, the separator, and then recover and recycle the carbon dioxide and hydrogen so we can use those to produce more product. It'd be terrible just to send those to a waste stream and to vent those from the separator. If we can separate them and recycle them, that's a much preferable. Look at this recycle stream. This recycle stream circulates 40 kmols per hour around and around through the reactor and the separator. By doing this, though, we can recover and reuse the raw materials and not lose the value of them. A bypass stream is illustrated here. In a bypass stream, a feed stream, the stream to the left there, is split into two streams. One of the streams will enter the process unit, and the other stream flows around it and is mixed then with the outlet from the process unit to form a product stream leaving to the far right. This is used for different purposes. One of the problems that will work is this stream is used to help preserve flavor in concentrated orange juice. Note that for a split point, the point to the left, where the feed to the process unit is split into two streams, at the split point we can write only one independent mass balance. That's because the composition of the two streams that leave that split point must be the same. If I take one process stream and divide it into two, the compositions will be the same, and the sum of the flow rates will be equal to the feed flow rate into the split point. Here's an example of a process that has a bypass stream. The bypass stream, you'll see why that bypass stream exists in this particular process. In this process, a stream containing 5.15 white % of chromium and the balanced water is fed to a waste treatment unit. The unit removes 95% of the chromium that's in the feed to the unit. That would be stream M2 if you look here. The unit has a maximum capacity of 4,500 kilograms per hour, and if the feed is greater than 4,500, the excess must bypass the unit. You cannot overload the unit. Now, this is undesirable, of course. You don't want to take some of this waste stream and not send it through the treatment unit, the waste treatment unit, to recover the chromium. But unfortunately, with the design of the unit, it's not possible to treat all of it if the flow rate is greater than 4,500 kilograms per hour. What we're going to do is finish labeling this flow chart, assuming that the inlet flow rate to the overall process is 6,000 kilograms per hour. Note that the 6,000 that's coming in, that's the flow rate associated with stream M1, is greater than 4,500, and so we can't send all of this to the waste treatment unit. A portion of this will have to be sent as a bypass stream around it and then mixed with the waste stream from the unit. The unit here, as you can see, produces a stream out the top, which is our recovered chromium, as well as a stream out the bottom, which will go to the waste, to wherever waste disposal we have, and that stream that comes out the bottom is mixed with what fraction of the feed that we can't treat. Now note that for a split, as you see here, is that if we split a stream, the split point that occurs to the left there of the waste treatment unit, that at the split, the streams that leave it must have the same composition. So if the mass fraction of chromium is 0.0515 in the feed, the mass fraction of chromium will be 0.0515 in both the streams that exit the split point. A split does not change composition. And so those two streams are labeled with the mass fraction of chromium, and the balance is water. So to get the water mass fraction, we subtract 0.0515 from 1 to get 0.9485. Now we're told that the maximum flow that can go to the waste treatment unit is 4,500. So we'll set M2 equal to 4,500. And we're going to apply an overall mass balance to determine that the flow rate of M3, the stream that bypasses this waste treatment unit, is 1,500. So 1,500 plus the 4,500 gives us a 6,000 total that is fed to the split point. Once again, that 1,500 kilograms per hour that's bypassing this unit is an undesired waste stream, and we would prefer to go back and redesign the waste treatment unit, but currently that's not possible. So what we're going to do is continue on labeling the streams, and we'll work our way next to stream M4 and see if we can label that one correctly. We don't know the flow rate of stream M4, so we're going to use the variable M4 to represent that. And we know that this is pure chromium. So the mass fraction of chromium is 1, and the mass fraction of water is 0. Next, let's look at labeling the stream M5. We don't know the flow rate. We don't know the flow rate of the stream, so we'll use the variable M5 to denote the flow rate. And we're going to use the variable X5 to represent the mass fraction of chromium. Since the two mass fractions must sum to 1, the mass fraction of water is going to be equal to 1 minus X5. Next, we're going to move on to labeling the stream M6. We don't know the flow rate of the stream, so we'll use the variable M6 to represent it. And we'll use the variable X6 to represent the mass fraction of chromium in the stream. Because the mass fractions must sum to 1, the mass fraction of water will be 1 minus X6. Now this process flow diagram is fully labeled. Let's talk about what control volumes we could use in order to solve for the unknowns here. There are 3 control volumes that we can consider. An overall control volume, the large red square that you see, a control volume around the waste unit, the medium-sized red square that you see, and finally a control volume around the mixing point, which is the smallest red square that you see. At this point, I'd like for you to determine the number of equations and unknowns associated with each of the control volumes. Just to remind you, the number of equations is going to be equal to the number of components, the number of different components that exist in the stream to enter or leave the process unit or the control volume. That's the number of equations. The number of unknowns we're going to get by simply working our way around the control volume, identifying the streams that cross the boundary of the control volume, and counting the unknowns or listing the unknowns associated with each of those streams. So why don't you take a moment now and try to do this on your own. I'm going to pause for a couple seconds to allow you to stop the presentation and do this. And then I'm going to continue with the results. What's shown here are the results of our analysis of the number of equations and unknowns. And I'm going to review how we got the results for the overall control volume. First, let's go around that control volume, identify the streams that cross the control volume, and in each of the streams, determine the components and the unknowns associated with it. So for the overall control volume, let's start with stream M1 on the far left there. In the stream, we find there's 2 components, chromium and water, and there are no unknowns. So, thus far, we know that we can write at least 2 equations because there's 2 components in that one stream. If we work our way clockwise around this control volume, we'll end up finding that stream M4 crosses it as an output from the control volume. If we look at this particular stream, it has only chromium in it. We've already included chromium in our component list, so we still have 2 components. But now we find that there's 1 unknown we have to add to our list of unknowns. That's the value M4. If we keep on rotating around clockwise, we find there's 1 more stream that exits from this control volume. That's M6. This stream has 2 components, chromium and water. So our component list contains only chromium and water. We have 2 components in total. Therefore, we can write 2 equations. We now have to add, though, 2 more unknowns. The unknowns associated with this stream are going to be the flow rate of the stream, M6, as well as the composition of chromium in the stream, X6. And there are no other streams that cross this control volume, so the total number of unknowns is going to be 3. Unfortunately, the number of unknowns exceeds the number of equations, and we won't be able to use to solve for the unknowns associated with this control volume. If we look at the control volume for the waste unit and for the mixing point, we find that we have the same conclusion, is that the number of unknowns is greater than the number of equations. So what do we do now? Well, now we have to go back and reread the problem and see if there's a piece of information that we can use to make one of the control volumes solvable. That will allow us to eliminate one of the unknowns or establish a relationship between 2 or more of the unknowns. So what is that additional spec? Let's go to the problem statement. The problem statement includes the sentence that the waste unit removes 95% of the chromium in the feed to it. So let's calculate the feed to the waste unit, the total feed rate to the waste unit of chromium, and then we'll take 95% of it. That 95% will be the amount of chromium that leaves in stream M4. That will be the flow rate of M4. The stream that enters into the waste treatment unit is stream M2. The total flow rate of M2 is 4,500 kilograms per hour. We'll put that over here in the table to calculate the 95% of the chromium in that stream. We have to multiply the total flow rate, 4,500, by the fraction of it that is chromium, which is 0.0515. So the product that you see over here to the right of 0.0515 times 4,500 is the flow rate of chromium in the stream that enters into the waste treatment unit. If we multiply that product by 0.95, that gives us 95% of it. The value is 220, it'll be kilograms per hour. That's going to be equal to the flow rate of stream M4, because we're told the waste treatment unit removes 95% of the chromium that enters into the waste treatment unit. Well, if we add this value, put this value of M4 onto the process flow diagram, and we go back and review our analysis of the degrees of freedom for each of the control volumes, what we find is that the overall control volume, we can solve for the unknowns associated with it. So let's start off with the overall balance for the overall control volume. So if we work our way around this control volume to determine the total amounts that flow in and out of the control volume, we'll start with the stream M1 that enters on the far left. It flows in at a rate of 6,000 kilograms per hour. So we'll put 6,000 into our balance equation on the left-hand side of the equals as an input. Let's work our way clockwise around. The next stream that we encounter is M4, and that's an output from the control volume. So we'll put the flow rate of that stream, which we now know is 220 kilograms per hour, on the right-hand side of the equals as an output. We'll continue working our way all the way around. We find that the next stream that crosses the boundary of the control volume is M6. That's an output, so we'll sum 220 and M6 to calculate the total amount that leaves our control volume. And if we keep on moving around our control volume, we find that we've now accounted for all the streams that enter and leave. This overall mass balance gives us an equation, an algebraic equation we can solve for M6, and we find that M6 is 5,780. Now we have M6. The last variable we have to determine is X6. And in order to do that, let's do a chromium balance. We're going to calculate the total flow rates of all the flow rates of chromium coming in and chromium coming out and set them equal to each other. We'll repeat this process one more time. Let's look at the control volume. We'll start at one point along the boundary of the control volume and work our way clockwise to calculate the inlets, flows, and outlet flows of chromium. We start with the feed, M1. It flows in with a rate of 6,000 kilograms per hour. We'll multiply that total flow rate by the fraction which is chromium, 0.0515, to calculate the amount of chromium, the flow rate of chromium into the control volume. So in our balance equation, we'll write 0.0515 times 6,000 equals, which is the input, we'll put on the left-hand side of the equals, and we'll set it equal to the amount that flows out. We work our way around the control volume. What we find is the next stream we encounter is stream M4. That's an output. And so we'll calculate the flow rate of chromium in that stream by taking the mass fraction of chromium, which is 1, and multiplying by the flow rate of that stream, M4. So we put 1 times 220, which we know is the flow rate of M4. We'll put that product on the right-hand side of the equals as one of the outputs from the process. We'll continue working our way around the control volume to find additional inputs and outputs. We find there's one more output. The flow rate of chromium in this stream is going to be given by the fraction X6 of the stream that's chromium times the total flow rate M6. And we're going to put that on the right-hand side of the equals. We'll sum that to the other output. But now that we know M6 is 5,780, we can write this as X6 times 5,780. If we keep on working our way around the control volume, there are no additional streams that cross the boundaries. We've accounted for all the inputs and outputs. And this algebraic equation then is one that we can solve for the mass fraction of chromium in stream M6. And if we solve this equation for X6, we find the value is 0.0154.